First of all, let's take a look at the user-defined functions that we'll be mapping. In this demo, we'll first explore how the various functions that we'll be working with were created, and then we'll execute them using the Server Explorer inside Visual Studio. We'll be looking at a couple of functions during this demo. One of them is an inline table valued function based on the select statement that we just used to create a view. Only this time we'll modify the query slightly so it only gets customer orders for a specific customer ID, which we'll specify as an input to the function. And then we'll look at a multi-statement table valued function that will return to us an overview of all statuses from the orders and the customers tables. And lastly, we'll look at a scalar valued function that calculates the total invoice value of an order. We're now back inside Visual Studio, and we'll start things off by looking at the migration scripts that have been used to create the user-defined functions that we shall soon interact with. The first one that we see here creates the get customer orders by customer ID inline table valued function, based on a query which is almost identical to the query that we used to create the customer orders view. As we mentioned during the slides, the only difference is that this query only fetches data for a specific customer. That this is an inline table valued function rather than a multi-statement table valued function is evident from the fact that its contents are entirely defined by the select statement that we see here, and that no table structure is defined. And as we can see, the function takes a customer ID integer as input, which it uses in the where clause of the select statement to specify for which customer data will be retrieved. And if we take a look at the next migration script that we see here, we can see that it creates the get status overview multi-statement table valued function. That this is a multi-statement function can be seen from the fact that a table called status is defined here, which will be the return value from the function. While a multi-statement table valued function might in fact contain just a single select statement, this one contains two. The first statement fetches the ID and the status of all customers in the customers table, along with a source caption that says customers. The next statement fetches the ID and the status of all orders in the orders table, along with a caption that says orders. Both of these queries are used to insert data into the statuses table, which will end up containing status information for both customers and orders. And as we can see, this function takes no parameters. But just like the inline function that we just looked at, we could have also defined parameters for this function. The last function that we'll look at is the get total invoice amount by order ID scalar valued function. Once again, we see a function that is simply defined by a select statement. In this case, a select statement that returns the total invoice amount for a specific order. And here we can see that the function takes an order ID as input, which is used in the where clause to determine which order to get data for. If we head over to the Server Explorer, we can see our three functions here. If we expand the get customer orders by customer ID function, we can see the columns that it returns. Here we see all the columns that we recognize from the customer orders view. And if we look here at the top, we also see the customer ID input parameter. If we now expand the get status overview function, we see the ID, status and source columns that it returns. And lastly, if we expand the scalar valued get total invoice amount by order ID function, we don't see any return values, only the order ID input parameter. Now let's try to use these functions. First of all, we'll try to run the get customer orders by customer ID function. As we remember from the slides, user-defined functions can be used inside select statements, so we simply run the function by using this select statement. And as we can see here, what we get back is data related to the orders belonging to John Doe with ID 4. Running the get status overview function is equally simple to do by running the select statement that we see here. And as we can see from the result set, we get status data back for all customers and all orders. The result is not very exciting at the moment though, since we've only defined a status for John Doe with ID 4. And lastly, let's try running the get total invoice amount by order ID function by executing the select statement that we see here, which returns to us the value 225, which is the total invoice amount for the order with ID 1. Having seen the functions in action on the database, let's take a look at how we can map them in our data model. And now let's take a look at how to map our user-defined functions. Before we dive into the demo, I just want to quickly make you aware of the pieces that go into the puzzle of mapping user-defined functions, and also to provide you with a quick word of caution for working with user-defined functions. But first, the pieces of the puzzle. So in order to map our user-defined functions, we first need to define fields in the CraftRock database context for retrieving data. We also did this for fetching data from tables and views by creating database sets containing the entities that were mapped to these. But for user-defined functions, we need to do things a little differently. For those, we'll instead define iQueryables to contain the entities that will map to the two table-valued functions and a method that returns an int for the scalar function. And then we'll map those in the onModel creating method using the hasDB function method. And then a quick word of caution. When we work with especially multi-statement table-valued functions, we must be aware of how they perform, since using them in the wrong way can cause a lot of overhead, especially when we're working with large datasets and many joins. Since the SQL Server compiler thinks of multi-statement table-valued functions as a table, they are treated as a black box, which means that the compiler doesn't take the interplay between the query inside the function and the surrounding query into consideration. This may lead to a lot of extra processing time since no cross-query optimization is performed and no benefits are reaped from parallel execution, and also the fact that context switching will take place. Historically, scalar user-defined functions have suffered from the same performance problems that plague multi-statement table-valued functions. But as of SQL Server 2019, scalar functions are automatically inline so that scalar user-defined functions are now treated as views, just like inline table-valued functions, which means that they are completely transparent to the SQL Server compiler and will be optimized as if the contents of the function were part of the query rather than a function call. And now let's dig into the demo. The first thing that we need to do is to create a collection for each of them that we can query. We'll do so here in the CarveLog database context. For the two table-valued functions, this is done by creating a virtual method that returns an iQueryable for each of them. The first one that we can see here will be used to map to the getCustomerOrdersByCustomerID function. And as we can see, this method takes a customer ID as input and returns an iQueryable containing the customer order entity that we also used for the customer orders view. And if we take a look at the expression part of this expression body definition, we can see that it consists of a call to the fromExpression method where we pass in a lambda statement that calls the method that we're currently defining. What this does is to create an expression from the call to that method, which will allow us to use the method to query the user-defined function instead of a regular DB set. The getStatusOverview function is set up in almost exactly the same way, except that its virtual method does not take any parameters, and the iQueryable it returns contains a new entity called StatusOverview. If we take a quick look at this entity, we can see that it contains fields to match the data returned from the getStatusOverview function. Here we see the ID, status, and source fields that corresponds to the columns returned by that query. If we return to the database context and look below here, we can see that the scalar-valued getTotalInvoiceAmountByOrderID method is set up slightly differently. First of all, it's set up as a method that returns an integer, and secondly, it has no proper implementation, just an expression that throws a not supported exception. This is because the body of the method is not important. The method will not be invoked client-side unless ifCore can't translate its arguments. If the arguments can be translated, ifCore only cares about the method signature. After having set this up, we need to configure the functions in the onModel creating method. The code that we see here configures the mapping for the three user-defined functions. First, we configure the getCustomerOrdersByCustomerID function. We do so by calling the hasDB function on the model builder instance. This method is used to map the virtual method that we defined above to the user-defined function in the database. The first parameter that we pass into this method is the method info for the virtual getCustomerOrdersByCustomerID method. And secondly, we pass in an array that contains the types of the parameters that the virtual method expects. In our case, there's only one parameter, the customer ID integer. The hasDB function returns to us a DB function builder instance, on which we call the hasName method to specify the name of the getCustomerOrdersByCustomerID user-defined function on the database. The same approach is taken to configure the mapping for the getStatusOverview and getTotalInvoiceAmountByOrderID functions, except for two details. The first one is that the getStatusOverview function does not take any parameters. But also notice here that we call the toView method when we configure the StatusOverview entity. This is because if we did not, ifCore would attempt to create a table for it, which we are not interested in. We're solely interested in using it for our user-defined function. By calling toView, we tell ifCore that the StatusOverview entity is mapped to a view. But unlike for tables, ifCore does not automatically create a view for us, and we do not need to actually create one on the database. This is similar to what we previously did for the customer order entity. But that entity we actually map to a proper view that we can query. This we will not do for the StatusOverview entity. We're simply doing this so ifCore will refrain from creating a table for us. Having set this up, we can head over to the program class in our console application and try running these functions. The first bit of code that we see here calls the inline table-valued getCustomerOrdersByCustomerID function, passing in the customer ID 4. And the next bit of code calls the same function, this time joining the results with the orders table. This is included to illustrate that we're able to keep composing on the query after we've called the table-valued function. The bit of code that we see here calls the multi-statement table-valued function, getStatusOverview. And like we did for the getCustomerOrdersByCustomerID function, we could have implemented further query composition after this call. The last bit of code that we see here fetches all orders from the orders table, and based on the result of this, it creates an anonymous type which consists of the order ID and the total invoice amount, which is calculated by calling the scalar-valued getTotalInvoiceAmountByOrderID function, passing in the IDs of the returned orders. Now let's run the code and see it in action. If we start by advancing the debugger step, we fetch the customer orders and can look at them here in the watch view. As we can see, we fetched 3 entries, just like when we ran the function on the database. And if we expand the first entry, we can see that it contains information about the first item in the first order for John Doe with ID 4. And if we now advance the debugger one more step and look at the customer orders by customer ID joined variable in the watch view, we can see that we once again get 3 entries. And if we expand the first one, we can see that we now have both the customer order information that was returned to us when we called the function, as well as the corresponding order that we fetched as a result of joining with the orders table. If we once again advance the debugger, we can see the result of calling the getStatusOverview function here in the watch view. Just like when we ran the function on the database, we get 5 entries back, and if we expand the first one, we can see that the customer with ID 4 has the status active, and if we expand the second one, we can see that just like we saw before, the customer with ID 6 has no status defined. And if we now advance the debugger past the last bit of code here, we can see the result of using the getTotalInvoiceAmountByOrderID function inside our select statement here in the watch view. And as we can see, we have data here for each of the 3 orders in the orders table, and the total invoice amount before VAT has been calculated for each of them. During the demo that we just saw, we looked at how we can map user-defined functions. We looked at mapping an inline table-valued function, a multi-statement table-valued function, and finally a scalar-valued function. Doing so required us to map our user-defined functions in the database to methods on our CarvedRock database context. We accomplished this using the hasDB function method on the model builder instance in the onModelCreating method. And lastly, let's look at mapping indexes using AFCore. Simply put, indexes are used to make lookup of data based on one or more columns more efficient. Just like we can use indexes in a book to quickly find a topic inside the book without having to search each page, indexes on database tables are used to quickly locate data without having to search each row in the database. When we create our entities using AFCore Code First migrations, AFCore defaults to creating indexes on primary keys and keys that are used in foreign key relationships. We can also use AFCore to configure new indexes on our table, which we shall see in the upcoming demo. So let's take a look at mapping indexes using AFCore. In this demo, we'll look at creating an index for the orders table on the name column. We'll also create a composite index on the customers table based on the full name of the customer, i.e. the combination of the first and the last name columns. We'll do so by configuring these indexes on the respective entities in the onModelCreating method.